everyone, welcome to Exploring Diana YouTube series where we explore the powerful capability of Diana one step at a time. My name is Solmaz and today I will go over to model one of the tutorials called column beam joint in a portal frame. Let me explain the problem and after that I will jump to the Diana environment to start simulating. On the screen, you can see the geometry of joint and reinforced arrangement. These joints are designed to resist moments and transfer loads. So understanding how much they can take before failing is really important and crucial. In this video, I will simulate an experiment to see how a reinforced concrete column beam joint performs under the assigned load. I will show you the setup including frames geometry, reinforcement assignment, and loading condition. And you can see everything step by step. Now I want to describe the summary of problem definition. In this problem, I will focus on the structural nonlinear, including both physical and geometrical changes. The horizontal load is applied to the beam through a loading plate and using the displacement control procedure. The main physical nonlinear behavior that I want to consider is concrete cracking, concrete crushing, and bond slip between the reinforcement bars and concrete. I will use a total strain based crack approach, and for tension, I want to use the Hordyke tensile K. In compression, the concrete strength is reduced due to lateral cracking and following a model by Vecchio and Collins. For the reinforcement steel, I will use von Mises plasticity by assuming isotropic strain hardening. And for the modeling the reinforcement, the two different assumptions are made to model the behavior of the bond between concrete and reinforcement. The first one is embedded formulation for the stirrups and longitudinal reinforcement in compression, and the second one is bound slip properties, which I use for longitudinal reinforcement in tension. On the screen, you can see the summary of material properties that I want to use during the simulating. Let me jump to the Diana environment to start the modeling. Alright, here we go. This is a Diana environment. At first step, I need to create a project. I call it portal. And I only need a structural analysis module. It's a two-dimensional problem. And for the measure type, I will choose the hexahedral or quadrilateral measure type. And for the order, I prefer the quadratic. And for the mid-side node location, I will select the on-shape. And now I will press OK. Just wait for a second until Diana create the project. Yes. Now I come to the unit and check the unit. For the length, I want to choose millimeter, and for the mass, I select ton. That's it. All is good. Now let me start the simulation procedure. Next step is creating the geometry. For creating geometry in Diana, you have three options. The first one is using the action toolbar. The second one is using the command console and the Python scripting. And the third one is importing model from AutoCAD. Just let me start with the polygon sheet to create the column and beam geometry. I call it column. In the method, I want to choose coordinate, and for the coordinate, I just easily copy and paste the coordinate from Excel to Diana. Yes. The second one is I call it beam, and again, same as the previous step, I only copy and paste coordinate from the Excel file. That's it. As you can see on the screen, I create the beam and column geometry. For the rest of geometry, I mean the loading plate and reinforcement arrangement, I want to take advantage of Python and scripting. For this video purpose and for saving time, I just copy and paste the Python script to the command console and wait for a second until Diana create the whole geometry, and now we can see the whole geometry. Just let me show you. Let's talk about the constraint which is used in this analysis. The first one that I want to constrain is the point which is located on the loading plate. I want to constrain this point in the X and Y direction. This assignment is because of the deformation load that I will show you in the next steps. For this purpose, I will come to the action toolbar in the support. I call it support. I call it deformation support. Let me let me define the support set. And the target type is a vertex. Now I select the one vertex of the loading plate, and now I want to fix it in the X and Y direction. Okay. The next step is tying. I will come to the action toolbar again, and in the tying, I call it tying deformation. Let me assign the tying set. And for the master, I will select the vertex of the loading plate. And for the slave, I want to select the edge of the loading plate. It's the equal type, and I will constrain the X and the Y direction for this point. With tying, when we use the tying, the deformation of this point and the outer edge of the loading plate are always equal. And in this manner, the load is distributed over the outer edge of the loading plate. Now I want to apply the load as a prescribed deformation. For that purpose, in the action toolbar, I come to the load. Let me assign the name. I call it prescribed deformation and set the load case for that. The target type is a vertex. The load type is a prescribed deformation. Now I select the edge of the loading plate, and the prescribed deformation is minus 1 millimeter in X direction. I will come to create. Yes, that's it. And the last support that I want to assign to the model is related to the base of the column. So I call it column support and assign the support set. The target type is the edge, and I select the edge of the bottom edge of the column. And now I want to fix it in the X and Y direction. And at the end, I will come to create. Now I want to assign the shape properties to the model. The first one, I want to select a column as a first object. In the element class, I will select a regular plane stress. For the material, I need to define the new material because I haven't defined any material yet. So I call it concrete. And in the class of concrete and masonry, I want to use the material model total strain based crack model. There is no need to select one of the aspects. Just click OK. And after that, I need to input the data related to the total strain based crack model. At first, I need to define the linear material properties for the Young modulus and Poisson ratio. For the total strain crack-based model, for the crack orientation, I want to select rotating, and for the tensile behavior, I want to select the Hordyke. And for the Hordyke, Let me input the tensile strength based on the table of material properties. 2.64, and for the tensile fracture energy for the mode 1, 0.137863. And for the crack bandwidth specification, I want to select the Gavin G, and its reduction model is a damage based. And also for the compressive behavior, I want to select the ideal compression curve, and let me input the compressive strength. And for the reduction model, I want to select the Vecchio and Collins 1997. And the lower bound reduction curve is 0.4 without no increase in the strength confinement. That's it. Let's go to the geometry. For the geometry, I call it column, and the thickness is 300 millimeters. Yeah. Now I can apply these properties to the column. The next element that I want to assign the properties is beam. In the element class, I will select the regular plane stress, and for the material, now I have a material that which I have defined it before, so I will select the concrete. And for the geometry, I need to create a new geometry properties. I call it beam, and for the thickness, I inputted 200 millimeters. Okay. Now I can apply these properties to the beam. This third one is loading plate. For the loading plate, I also choose the regular plane stress. I need to define the new material properties. I call it loading plate. And in the class of the ST, I want to select the material model linear elastic isotropic. In the for in this window, I need to input the linear material properties for the Young modulus and Poisson ratio. And for the last step is the geometry. For the geometry, I want to consider the loading plate geometry, same as the beam. Now I can apply these properties to the loading plate. After defining the material properties for the beam, column, and loading plate, I need to assign the reinforcement properties. Let's start with the inner column reinforcement. In the action toolbar and in the assign category, I will select the reinforcement properties. The type is the embedded bar, and for the material, I need to define the material for this reinforcement. I call it main reinforcement embedded. The class is reinforcement, and material model, I want to select the von Mises plasticity. Now I need to input data for the linear part, Young modulus, and for the von Mises plasticity. The plastic hardening, I want to select the total strain and yield stress. And for the diagram, I just need to copy and paste data from the Excel to the diagram. Yeah, that's it. For the hardening hypothesis, I will select the strain hardening, and the hardening time is isotropic hardening. Now I will go over to define geometry. For the geometry, I call it the main embedded And for the cross section, I need to define the cross section of the embedded reinforcement. Okay, that's it. Just need to go to update button. Yes. In the next step, I want to assign the reinforcement properties for the bottom beam reinforcement. I will select the bottom beam reinforcement in the left toolbar and just going to the reinforcement properties. The material is main reinforcement embedded and I need to define the new geometry. Bottom embedded. And now I need to input the cross section for the embedded reinforcement. And now update the properties. In the third step, I want to assign the material properties to the reinforcement, which I want to consider them as a bond slip reinforcement. So in the outer column of I want to select the outer column reinforcement. I will go over to reinforcement properties. In the type, I need to select the circular beam bond slip bar. And also I have to assign the new material properties. I call it main bond slip. It's a bond slip reinforcement. And in the tab of material, I need to define the material properties for the Young modulus, Poisson ratio, and for the nonlinear model, I want to select the von Mises plasticity. And then for the hardening function, I want to select the total strain, yield stress. And also I need to define the diagram for the strain, the total strain, yield stress. For now, I just copy and paste from the Excel to the diagram. Now I will go over to the next tab, bond slip interface. For the normal stiffness modulus, I input the 1000 Newton per cubic millimeter. And for the shear stiffness modulus, I input the 100. And no failure for the bond slip interface failure model. Now for the geometry, I need to assign the new geometry. I call it outer bond slip column. And in the reinforcement type, I need to select circular beam bond slip. And the diameter of the circle, I need to input data related to diameter of the circle. That's it. And I need to update the properties. Last step in the reinforcement properties definition is related to top beam reinforcement. I will open the reinforcement properties window. The type is circular beam bond slip bar. For the material, I want to select the main bond slip. And for the geometry, I need to assign the different diameter for the top beam reinforcement. I call it top beam. Now in the reinforcement type, I select the circular beam bond slip. And for the diameter of the circle, I need to input the diameter of the reinforcement. Now I need to update the material properties. That's it. The last step in material definition is related to STIRO, which are grouped in a reinforcement set, which I call it stiro. Just select the stiro set, and in reinforcement properties, I will select the embedded bar for the type, and for the material, I need to define the new material properties for the stiro. I call it stiro, and is a reinforcement. Material model is a von Mises plasticity. Now I need to assign the Young modulus for the linear elasticity behavior. And for the von Mises, I want to select the total strain, yield stress. And for the diagram, I just only need to copy and paste the data from the Excel to the diagram. Yes, that's it. Very nice. And the hardening hypothesis is a strain hardening. For the geometry, I call it stirrup again. And in the embedded type of reinforcement, I need to define the cross section of stirrup. Now I need to update the reinforcement properties, and up to now, I assign all material properties to the whole part of the model. In Diana, you can review what you have done until now in the left toolbar. For example, in this model, I have assigned and defined the geometry for the concrete elements and the reinforcement elements. Also material for all type of element that I have in the model. Also the supports for the loading plate and the bottom of the column, loads, and tying. Now I have only one step behind the analysis setup. I need to define the connection between the loading plate and the beam, and also the bottom of the column. For this purpose, I come to the connection. I will set the name loading edge. The connection type is interface and mode is close. For the source selection type, I want to select the edge, and for this purpose, I will select the edge of the beam. For the target edge, I want to select the edge of the loading plate. So only I show the loading plate and select the related edge. For the element class is a structural line interface, and I need to define the material and geometry for this type of interface. Let's start with the material. I call it linear. It's the interface element and linear elasticity. The type is 2D line interface. For the normal stiffness modulus, I input the 1000, and for the shear stiffness modulus, I input the 10. Goes, and I will go to the next one, defining the geometry. I call it also the linear. It's a line and 2D line interface element. I input the thickness same as the thickness of the beam. That's it. Now I can create this interface. The next connection is related to defining interface at the bottom of the column. To replicate the experimental setup, we use nonlinear interface element at the base of the column. So by defining these elements, we allow the column edge to rotate freely, just like what happened in the test. So let me show the other elements on the screen. Let's start with the setting name. I call it nonlinear. The connection type is a boundary interface. And for the edge, I will select the column base. That's it. The element class is a structural line interface, and I need to define the new material and geometry for this purpose. For the material, I call it nonlinear. It's an interface element. And for the material model, I want to select nonlinear elasticity. That's it. Let's start with the linear material properties. It's a 2D line interface. For the normal stiffness, I input the 1. And for the shear, I input the 10,000. And for the nonlinear elasticity, I want to select the no tension with shear stiffness reduction. The no tension condition combined with the low normal stiffness helps us simulate the free rotation at the base. Meanwhile, high shear stiffness is used to prevent any horizontal movement of the column. So let me define this material. And I will go over to the next one, geometry. I call it again nonlinear. It's a line, 2D line interface. And for the thickness, I input the data same as the thickness of the column, 300. That's it. And now I can create the nonlinear boundary interface for the column base. For the sake of saving time, I will only walk you through the setup process for the analysis and then review some of the key results together. For this purpose, I have prepared a file in advance that I will be using. Let me show you the next one. Okay, let's have a quick review on analysis setup. It's a structural nonlinear analysis. For the nonlinear effect, I selected the physically and geometrically nonlinearity. And for the load setup, I considered two different load patterns for the load step. Yeah, that's it. So let's have a quick review on the results together. For the result part, let me show you the total displacement in XY. Yes, as you can see on the screen, the result is related to TdTXY. Also, I want to show you the reaction forces in the X direction. For this purpose, I select the node exactly under the prescribed deformation, and the show table. In this table, you can see the reaction forces in X direction in each load factor. Also, we can see to see the development of the crack. For this purpose, I will go to the crack width, and the result is shown in the integration point. Okay, just let me show you the crack propagation in different load steps. For example, the step 20, load step, for example, 178, load step 400, and the last step is 480. As you can see, the crack is propagated through the concrete portal frame. And also, I want to show you the principal strain in this model. For this purpose, I will go over to properties to set the specific value. And you can see the principal stress E2 in different load factor. For example, in the 400. Yes. This is the E2 at load step 400. As you can see on the screen, there is a very good agreement between the Diana result and what happened in the experimental At this moment, the simulation is finished, and I want to show you how you can find these related tutorials on Diana website. Just let me open the Diana website. In the Get Started section, please go to the tutorials. And in tutorials page, based on the tutorial type, analysis type, and modules required, you can find your desired tutorial. For example, for now, I want to select the technical structural, and for the analysis type, I want to select the structural nonlinear analysis. Please load more tutorials, and that's it. It's a column beam joint in a portal frame tutorial. Thank you for your attention. Please subscribe the Diana YouTube channel and don't forget to tune in for the next video.